In this room, we've got Managing Peak Electricity, Approaches and Technologies for a Rapidly Electrifying Future. For those of you who were in the other room for the last few sessions, my name is Andrea Linsky, and I'm the Director of Emissions Neutral Buildings at Alberta Eco Trust Foundation. I'm not going to introduce too much of ENBIX right now, but I will tell you all a little bit of, we had someone come up to me just a few minutes ago and say, hey, how do I get one of those cool ENBIX pins? And I said, well, you have to share information. So ENBIX is about sharing knowledge that you have around emissions neutral buildings with your peers. So our panelists today will leave today with their ENBIX pin because they're here sharing information about our buildings. We've got a few of our executive advisory committee members in the room who have pins. So if you want to get a pin and you have information about emissions neutral buildings, come and approach us. We'd love to have you share that with us. This panel, we actually have just two panelists that are going to get into some details around peak demand. And before I get too far into introducing them, I'd like to talk a little bit about our resource library we have at ENBIX. I think I mentioned it earlier, but one of the two big pieces of work that we're going to talk about today, we have in our resource library. It is the Electrification Without a Service Upgrade report that was written by Frank and the Passive House Alberta team. And so if you want to get into the details beyond what we discussed today, please take a look at that resource. We have a few more great related studies coming your way very soon as well, as a bit of a teaser. I'm sure Frank will talk a bit about that as he does his work. I'm going to go back up to our panelists slide here. Perfect. So our panelists today are Frank Crawford and Chirag Mehta. And I'm most excited to be here today because I deal with peak demand issues related to deep energy retrofits all the time, both in my professional work and in my private life. And I'll talk a little bit about that. So prior to coming to Alberta Eco Trust Foundation, I worked for the City of Edmonton as their corporate climate management lead. And so it was my job to help figure out how we were going to decarbonize all the buildings that were owned and operated by the City of Edmonton. And one of the number one barriers that we run into with almost every project, the City of Edmonton actually has a sustainable building policy that basically says any new construction that happens that are city-owned buildings must be net zero or emissions neutral buildings. And so that was all well and good if we're building a library, but what about when we're building a bus barn with a bunch of electric buses? Or what about if we're building a fleet building that has a whole bunch of electric vehicles? How are we going to deal with the peak demand related issues associated with those buildings and the upgrades to the systems that are required for those types of buildings? So it's something that we discussed quite a bit while I was working with the city. And then at home, I'm going to one up Shane from earlier today. I am also doing a deep energy retrofit on a private home, my private home. But in this house, we are putting 3 fully electrified units into one 200 amp service. And so this is yet another challenge where we're trying to densify, take what was a 1950s single family bungalow and turn it into 3 units. And do it all without upgrading our services as well. So it's something that I have spent a lot of time and for a single house money on electrical engineering for. And I'm hoping to be able to share that information and the information that Frank will talk about a bit as well about how we're going to deal with that with the City of Edmonton as we go ahead with getting these retrofits done. I'll start by introducing our panelists here. Frank is a civil engineer, a certified passive house designer, and a tradesperson. And through his work with energy efficiency as an energy efficiency consultant and the education committee lead for Passive House Alberta, he helps others build or renovate to a high-performance construction standard while minimizing carbon and cost. And Chirag is a highly credentialed expert in the design and development of energy performance contracting projects. He brings with him over 10 years of engineering experience with the Johnson Controls Western Canada team, and possesses experience in engineering, facility operation, and project management. And as a professional engineer, he's completed over 20 recommissioning studies for commercial, institutional, and laboratory facilities. So today, our presentation is actually two longer format presentations from each of Frank and Chereg, and then we've got some open questions from the floor, so please do send in your questions as they come up for our panelists. So I think it's Frank's presentation we have up first. We'll find out. Nope. Chereg, come on up. I got a head shake from the back of the room.
Good afternoon, everyone. Can you hear me? Perfect. Okay. So my name is Chirag Mehta. I work at Johnson Controls as an energy solutions development engineer. I've been there for just over a year and a half, but as mentioned, I've over 10 years of experience in the industry. Today, I'll be just talking to you about how we help our clients reduce their peak demand load on their commercial facilities, and what kind of strategies we implement over there. Perfect. Just to quickly go over, I'll explain who JCI is in case some of you don't know. Why demand is important, at least to our clients that we work with, how we reduce demand for them, and how we make demand savings work for them too in the source of revenue. So a lot of you know Johnson Controls through our services of BMS, such as Medisys, but underneath the umbrella of Johnson Controls, there are also brands of Tyco, York, OpenBlue, and many more, but those are just to name a few. But the team I work with is Sustainable Infrastructures, and it falls underneath the umbrella of Johnson Controls, but we're systems agnostics when we work with any client that comes to us or that we seek out. So when we do work with clients, we basically work with them to decarbonize their built infrastructure. That includes HVAC systems and electrical systems. We perform investigations, energy audits, and we strategize a roadmap to GHG reductions, energy savings, and cost savings as a byproduct. We achieve this through turnkey design build, as a prime contractor on the site, and guarantee the performance. We help our clients source financing to make these upgrades necessary to achieve their goals. We develop, implement, and we do performance monitoring. So demand management itself for our clients, it's important because, as we know, a big chunk of the utility bill that we do get, up to 50% or sometimes higher, is demand charges. It just happens to be in Alberta specifically that it's hidden in the distribution and transmission fees, as opposed to our counterparts in BC where it's readily available, readily seen. This month's demand is 500 kilowatts, or it was 500, but you had a peak of 800 in prior months. So it's very relevant and very prevalent to dive into and see where these demand charges are taking place. The other thing is also that we have to take into consideration is the ratchet. Any peak demand that a client experiences stays with them for the next 12 months in the form of a ratchet at 80% of that peak. In addition to that, a lot of our clients that we work with have a contract agreement between the utility company and themselves in the form of a MDA, a minimum demand agreement. And any savings that we may achieve from reducing demand, if we do not address the minimum demand agreement that's in place between the utility company and the client, will not be realized by the client themselves. Their charges and their demand will still be high. And it needs to be addressed. So unless we address that, we can change as much as we want, but if the demand agreement is still in place, they will still experience high distribution and transmission fees, will start to make up a bigger portion of their utility bill. So going into a specific case study, hopefully people can see this. What we have over here is a client in Alberta that we're working with. This is the interval data from the client on a 15-minute interval basis for the full year of 2019. Over here we can see the red line represents their MDA, minimum demand agreement, and that is at 4,300 kilowatts. And we can see during the summertime, their peaks average about 2,000. It's less than 3, above just around 2, but overall for the year average is around 2,000. But they experience peaks as high as 5,500 kilowatts. So what that means for the client themselves is their ratchet going, and that peak actually happened to be in the end of December, the end of the year in December itself. So what that means is they'll have a ratchet of 4,400 going into 2020. Even if their load profile looks similar to what it is in the summer, they will still be charged a demand of 4,400 for the year 2020. And this is important for us to know because as the consultant looking at this site, we need to understand what process loads are causing these spikes and how can we mitigate them going into the future and reduce it to a more flat line. So when we look at any client such as that or anybody else, we have a typical load profile for a building, which is represented by the graph on the left, which starts off relatively flat, peaks in the noon, and then tapers off, coinciding with the schedule of the building itself. Our first goal is to reduce that load to the yellow graph through strategies which I will explain in the coming slides. The second step is for us to start generating energy on site. And the most prevalent way is through solar. I mean, there's generators and CHP, but we're looking at solar as the next step forward, sustainable, and also we live in Alberta and we can take advantage of that. But with solar too, before sunrise and after sunset, the site still experiences peaks, which we can see in the graph, in the blue graph on the right. And those peaks, once again, will stay with the client going into the next 12 months. So the goal for us is to reduce those peaks even with solar integrated into the site. And we can achieve that by implementing storage on site, as discussed previously. And storage on site, best used with batteries, can help flatline the demand profile of the site in the graph on the far right. So the goal is to go from a peaky load on the left side, which we see, which is more traditional, and shift as much as possible to the right, making the utility billing more predictable for the client, more flatline, and allowing them to renegotiate their MDAs as I described previously. Now, not all clients have MDAs. The ones that we work with, big clients do, and it's kind of nestled into their utility contract, and it can only be viewed and analyzed on the online portal itself. So the most prevalent and easiest one for a lot of clients that we also propose, and clients themselves are taking the initiatives underneath their own accord to implement without any external consultancy, is lighting. It's easy, effective, and a lot of contractors are able to implement this with in-house engineering. It's able to save 40% on the end use of electricity itself because we go from 32 watts traditional T8s to 15 watt LEDs, and also other, whether it's lamps, wall packs around the building, very efficient to upgrade. And then you combine that with lighting control systems to further propagate energy savings, demand savings with lighting end use specifically. The next strategy we look at usually is system optimization, and this requires a skill set from engineering companies with the introduction of recommissioning or retrocommissioning of a facility to look at HVAC systems to reduce energy consumption. This comes in the form of reviewing occupancy schedules, time of day use, operation between summer and winter, enabling systems to make sure they're not fighting with each other. Heating, cooling systems don't fight, and implementing night setbacks. All of these strategies help reduce their peak and shift the graph down for the client. By doing this, will allow us to start implementing and introducing electrification of their systems for heating the building itself, because we know electricity in Alberta is becoming more efficient in terms of greenhouse gas emissions, but natural gas is pretty steady state. And by introducing off-peak electric boilers, we can ensure that the peak demand for the site does not increase. It also reduces the chances of us having to do a service upgrade, which can be very expensive, and at the same time puts them on the roadmap towards decarbonization. Now, after doing this, as I mentioned, we introduce sustainable generation to the client in the form of solar and batteries. And as we know, as I demonstrated in the previous slides, solar generation is not taking place at all the time. It's not taking place all the time. We still experience those peaks, and we want to reduce and flatline those. So we introduce battery storage, because any excess energy produced by solar on site can be stored in the batteries, and the client now has the option and the ability to decide whether they use this energy on site or whether they sell it back to the grid as a source of revenue for themselves. Alternatively, generators and CHP are also an option combined with sustainable fuels to reduce greenhouse gas emissions and a source of managing peak load. In addition to that, these pieces of equipment also are great to participate in the operational reserve market as a source of revenue for the clients also, especially as demonstrated in some of the previous presentations when we got that emergency notice for everyone to turn off their lights back in January, if I remember right. Companies that participated in this would have had a source of revenue generation, and we present those options to clients also. So now if we look at it, you work with a client, you upgrade the lighting, you recommission the site, you optimize the building's operation for HVAC and electrical, you introduce solar, and you introduce battery storage. To tie all of this together, a grid interactive efficient building is the next step, and is the next step that Johnson Controls is also working and developing software for. It's, as we mentioned previously, if just like a BMS system works to control the heating and cooling systems of a building and the ventilation to provide comfort to the occupants within the space, a grid interactive building works between the grid and the building to optimize demand that's consumed by the facility. It's the next step to move forward with. This is just a representation of how that looks, but it's a work in progress. It's still in development. But it's basically, think of it as the BMS system that's in the building to control the HVAC and equipment, but it's now between the grid and the building to manage the energy that comes to the facility. It allows the client to decide when and how they use their stored energy or energy produced on site, whether to sell it, store it, or consume it. Thank you.
Perfect. So we'll have Frank come up now and talk about residential related applications. A little smaller, but same problem. Thanks.
All right, so I'll probably talk fairly quick. I've given this speech a few times, and as Andrea said, this lives on the ENBIX resource page, so you can read the longer full report on it. but kind of talking a bit about how we could go about electrification without a service upgrade, generally at a residential level. There's me again. So here's some kind of opening remarks. So the grid, unfortunately, in Alberta is still fairly dirty, fairly high in fossil fuels. So if we do want to get those on-site carbon reductions, we need those on-site renewable generations to get it. And often, when we're looking at kind of those peak loads for a residential building, our peak loads are going to probably be similar to what our design heat loads are, plus a little bit of like consumption, cooking, and EVs. But as we lower those design heat loads, our peak load should go down at the same time, assuming we are electrifying our building, so the peak load would be electrical as opposed to natural gas. So really, we wanted to start with that high-performance building. As it's been said a few times before, the most efficient electron is the one you don't generate because of efficiency. So start with the envelope, and then after that, if we add those electrical EVs, or sorry, add the solar panels, if we don't start with the envelope and just add a whole bunch of site solar, we're going to have a big solar peak where we're selling lots back to the grid, but we're still going to need to draw a whole bunch from the grid in the winter, which kind of adds to that winter peak. So that's why we want envelope first and then on-site renewables. And as we're doing this with deep energy retrofits or just high performance all electric homes, what we're seeing is the default route is we put a 200 amp service in. And what the reports that I've been writing have been seen from others is that we really don't need to do that. But why? Why are some reasons? So first of all, we want to avoid that cost. So depending how fast, whether you're the first on the block, to upgrade to a 200 amp service, it's still going to be either $5,000 to $7,000 because and that's if the transformer is close by, the transformer has capacity, and you have an overhead electrical line. If you have either an underground line or the transformer is full, it can very quickly get into the $20,000 or plus $1,000 for that upgrade, and then generally electrification just dies right there. But then there's also societal downsides or societal benefits if we don't upgrade. The utility grids have to meet the demand. So if we keep putting more demand on it, the utility grids are just going to have to get bigger. And to some degree, the utilities, and I didn't realize some of them are in the room, would like to do that because they get then to charge us for all that work that they do. Those are our fixed demand charges. That's how they recoup the cost to make the grid bigger. So if we all say we want 200 amps, we're all basically saying we want the grid to be at least twice as big, so the grid is going to have to get twice as big, so those demand charges are going to go up. So for individual and societal costs, we want to try to avoid that 200 amp upgrade. So stay on 100 amps. So how do we do that? These are the very basic steps. The report has more details. We go on a watt diet. We use load share devices. We use smart electrical panels. And then for our solar PV generation on site, we either split the electricity using a type of splitter or a larger bus bar system. And then the details are in the report, but I'll go over them briefly. So the watt diet, I didn't come up with it. Generally, the people in California, Redwood Energy, came up with it, and it's just basically a bunch of processes you can go through, kind of steps you can go through that's fairly easy to how do I reduce that calculated peak? Because the calculated peak is based on a whole bunch of code clauses in the electrical code, and you can't really get around that. You can change what you do to try to reduce that calculation, but eventually you have to do the calculation and you can't get around it. So what are the steps? The first step, the easiest step that I always recommend first for a residential home is that start with your biggest load, which is generally your electric dryer. Right now, your electric dryer is probably going to be a 30 amp, 240 volt circuit, pretty big. So if we just swap that out for an all-in-one washer and condensing dryer, or just a condensing dryer, which now no longer needs that large circuit, then we can drop that load from the 30 amp 240 volts down to 15 amp 120 volts. So that's a pretty big drop. And the other nice thing about the all-in-ones is because then you put in dirty clothes, and about 3 hours later, you get clean, dry clothes out. So you no longer have to switch it from one appliance to the other. And the other nice thing is, this is just from Home Depot, the one appliance kind of costs the same as each of the two appliances you have to buy if you bought a separate high-performance washer and a high-performance dryer. So it's one of those few times where cost and convenience and time and electricity and savings all actually give you the same answer. So start with this. Next is the envelope. So perform either a deep energy retrofit, we call it DER, but there's a few acronyms that use that one, so a deep energy retrofit, or just build your high performance envelope, do an energy model, but roughly speaking, we want an air changes below 1. We want about either adding 6 inches of insulation to our existing wall or about an R30 wall, triple pane high performance windows, insulate at least 1 foot below grade on a retrofit, or all the way down to the foundation is better, but not a ton. And if we have an attic, most of us have a vented attic in our house at home, insulate that up to about R80. So those are the very basic ones, and because of that, then our peak heat demand will be somewhere around that 8 kilowatt range, which is almost the same size as that electrical savings we got from going to electric dryer to that heat pump dryer. So that 8 kilowatt range is about a 30 amp circuit, 240 volts. So it fits on that same space you just created on your electrical panel. And then next we can fully electrify our HVAC system. We do this with a heat pump. Heat pumps do work in our climate. Below -25 or -30, if it's an air source heat pump, it is likely going to be needing some secondary heat to assist it. But if you have a ground source heat pump, because it uses the ground, you don't need any supplementary heating. But they do work. My house has one, a number of other houses. It's not an if, they do work. And that's how you electrify it, and that's how you get heating and cooling. Next, you want to make sure you are adding that ERV, that energy recovery ventilator. This provides you the fresh, filtered, conditioned air. The air sometimes is clean, but as we probably all remember, smoke season, it often isn't. So we want that filtered, fresh air coming through the ERV. And then the other thing that we've learned from both this study and a new study we're doing kind of right now is when we're commissioning that cold climate air source heat pump and the secondary heating system, we want to make sure that there's an actual control so that we use one or the other, not both. Because at some point the air source heat pump is no longer efficient and we should switch to the secondary. We don't want both to be running because then we can increase the peak load. We have 2 large systems running as opposed to just one or the other. And that secondary heating system, we prefer to be electric, but in some cases, fossil fuel is still a good option. And then if we've done all of that and we do the electrical code calculation and we're still over that 100 amps, this is when we start to bring in what's called load share devices. Load share devices are any device that allows you to add an additional appliance to your electrical panel without impacting that code calculation. And it does that by controlling when that connected appliance turns on and off. And there's 2 basic types of them. This is another place where kind of nomenclature will vary. The most common words I've used is a primary and secondary load share device. This just has 2 ones and one or the other works. Or a circuit pauser. This is where it just monitors the main and either turn on or off that connected circuit. But basically, it's the 2 ways to control this additional appliance when it can turn on. And the nice thing is these things only cost like $850 to $1,300, 1 or 2 hours to install them, so pretty low cost. You do need to use an electrician and you do need to take a permit, but pretty low cost. If after doing those load share devices you still don't quite make it onto 100 amp services, then you could use what's called a smart electrical panel, or as maybe the prices in these come down, they become more prevalent. Smart electrical panel is just basically a load share device on every single circuit. So every single circuit is controlled, monitored, prioritized, and then you can also utility bill for it. So they're a good option if you need more than one load share device to stay on 100 amps. If your home is integrating a whole bunch of batteries, backup generators, solar PV, EVs, if it has a whole bunch of different things that need to talk, using these smart panels is kind of that center that allows everything to talk together. So it's a good option for that. Or if you have multiple units. Example, Andrea's, you could have one smart panel that controls 2 or 3 units and gives them power as needed to still stay under that 100, or maybe with 3 units, maybe 150 amps. The reason is you don't want to go to these to default is they're relatively expensive. It's about $5K for one of these smart electrical panels, and it's probably $3,000 to $5,000 to install it, so they're still a bit pricey for just a single family home. But for more complicated options, it's still a good option. So that kind of deals with all of the generations and consumptions, but now, as I said, we want that on-site solar production. So how do we get that big solar PV system onto it? The problem is with a solar PV is not actually how much energy it consumes, because it doesn't consume anything. It's a production. What it needs is a larger bus bar. So there's a few ways to do that. We can use a splitter, which basically splits your incoming electricity to the panel and to the solar PV. This can be done at the meter base or just after the meter base. Check with your local provider to see which splitter option is available. Or we go to the panel and get a larger bus bar. So the rating of your panel, that's that number that's on the sticker somewhere on the panel, that's the rating of the bus bar. And that sets how much, there's again another code calculation, how much solar you can put at the bottom. So you could put in a larger panel with a larger bus bar, but then still use a smaller 100 amp breaker, so that you still only are taking 100 amps from the grid, but it gives you that larger connection to put a larger solar feed at the bottom. And here's just some calculations with your 125 amp service, or 125 amp bus bar and 100 amp service, or a 200 amp bus bar and 100 amp service, which will two options if you have to replace the panel, put in a bigger panel, but still keep that 100 amp breaker. And again, confirm this with your local code inspectors to make sure it's acceptable before you go out and buy the equipment. So the next kind of part that we've done to this is we're doing another small survey to kind of see what the actual peak loads are, because we've seen from kind of the math that the calculated peak loads can make it on 100 amps. So from that, we've all been talking about that January 13th grid emergency, so we've gone and got some survey data from a number of high-performance all-electric homes, and the preliminary data results from that is the highest peak that we got was 25 kilowatts, which is just over 100 amps. 100 amps should be about 24 kilowatts. But that peak included 8 kilowatts of EV charging. So if we stuck that 8 kilowatts of EV charging on that circuit pauser and changed when it occurred, then all of the surveyed homes could fit on 100 amp service. Most of them are falling in the kind of 10 to 15 kilowatt range, which is still much below that theoretical 24 kilowatts on 100 amp service. So from both the theoretical calculation and the actual data, we should be able to stay on 100 amp service if we're using that EV or circuit pauser to control the EV or any other large load that might happen at the same time. So there is no code reason why we can't stay on 100 amp service from the calculation reason, and what we're seeing from the data is there's no actual measured reason why we also can't stay on 100 amp service. So hopefully we can try to do that and not have to double our electrical grid size. That's it.
Great, so we have a few questions coming in here. Let's see where we can go with this. So the clarification question for you, Frank. With the load share devices or smart panel, will it prevent you from using some devices at the same time? For example, it can't charge your EV while you use your stove or dryer.
So yeah, it depends. With a primary and secondary load share device, whatever's primary always has power, and then the secondary device that's attached only has power if the first one is off. So those are good for if you have two things that don't want to occur at the same time. The circuit pauser monitors the main. So as long as your main is under, generally they set it at 80%, so as long as your main is under 80%, then whatever is connected to that circuit pauser will run. So in most of the summer, when your air conditioning peak is probably lower than your heating peak, you can charge whenever you want. In the middle of the winter, there might be times when your heating system is running and you're cooking dinner and you're running your dishwasher and your toaster running that you can't charge your EV. But those don't last very long, and then overnight, maybe your heating load is running, but if your heating load is still down in that 8 kilowatt range, you still have 12 kilowatts or whatever left of EV charging. So yes, there is some constraints, but as long as you're doing that envelope first to drop your peak heating demand, or using a ground source heat pump to still reduce that peak heat demand, then you should have time to charge whatever you want.
Okay. So we've got lots of questions about that. People want to know what to do with their house, Frank. So here's maybe a more theoretical question. Maybe we can apply it to both, potentially both homes and commercial buildings, although this probably doesn't happen for commercial buildings. It says some homes have gotten service upgrades at no cost. Should we be moving away from free service upgrades to incent more peak load management? Maybe I'll twist that question a little for the commercial side and say, like, how can we incent load management better in commercial buildings as well? So maybe we'll start. Yeah.
It's actually kind of hard. Yeah, I'm trying to think about that one. A lot of clients that we do work with, they want to electrify their systems and processes at their commercial facilities, and primarily it's always the heating systems, going from natural gas boilers to electric boilers, and a lot of the times the electrical infrastructure at the facility is insufficient to accommodate those kind of upgrades, because a lot of these commercial facilities, putting a boiler in will be a massive load increase to the facility itself. And the upgrades that take place to increase the service to the site runs in the millions of dollars, not just a couple of $100,000. So I really don't know the best strategy to incentivize them to do that. Maybe it's a question of distributing that loan over a longer period, similar to how we achieve that for equipment pieces, or building it. Or another way to do it is to create a project with a lot of low-hanging fruit with quick payback, so that the longer-term payback items such as electrical service upgrades, boiler upgrades, fuel switching, can be nested into a larger project where the payback period is 15 years or 20 years, and the service upgrades get nestled into that project itself.
All right, I guess I'll take a run at the rebates. So yeah, we're past the pilot stage. We're trying to get into the mass adoption stage. I think there is still a need and a good overall use of like tax dollars to provide the rebates for retrofits. I think they need to be a combination of ones where it's less pay up front, so adding in that equity piece where they go to just one company, the company comes in and kind of as a retrofit coach, kind of helps you do all the steps and provides some of the funding for it, because deep energy retrofits are expensive. There's no really way around that, but way to finance them over longer periods and to allow some of the lower income people to still enjoy the benefits of it is another good use of those tax dollars. So yeah, I think until the industry moves toward high performance just being standard, we still need some carrots. We've been liking the carrots and sticks today. We still need more carrots to get people to do it. The carbon tax is a good stick, but it's not a big enough stick on a residential scale to really make people go there.
We have a commercial question. So what commercial building systems are good fits for load shifting?
It comes down to analyzing the building itself to see what systems are in place that are critical to the operation of the building and which systems are not. Sometimes an easy change could be temperature adjustments to occupied spaces, such as increasing or decreasing the temperature depending on the time of year. And throttling potentially ventilation as long as it's within the parameters of what's acceptable by code. Those are, right up the top of my head, systems which can be throttled effectively. It comes down to the client reviewing the systems that are also in place, and the consultant also helping the client determine what systems in the building are not critical to the operation. It could be lighting, it could be ventilation, it could be space heating and cooling of a given area, to help throttle down and manage peak shaving.
Thanks. Frank, we've got a question about how if cities want to help electrify or reduce demand, would it make sense to allow for load sharing devices to be installed without a permit, or to allow an electrician to verify? And so I guess the question is not just that, but is it purely at the addition of those load sharing devices that are requiring the permitting process, or are you usually having to do that for other pieces when you're doing these retrofits as well?
You're touching your electrical system, so get a permit. Yeah, you're touching your electrical system, use an electrician, get a permit. If the city wants to put an incentive, they could waive the fee on the permit. But generally, if you're doing like a full deep energy retrofit or any large renovation to your house, get one electrical permit and you can put a whole bunch of things on it. You don't need separate permits for each one of these things. But no, use an electrician. We want to make sure it's done right. If you do it wrong, you'll burn your house down. So get an electrician, do it right, get a permit. Just combine it with everything else so it's only one permit.
Okay. Another question, Frank. Would you say an average electrician knows about all these different measures that are out there? And if not, do you see this as an education issue?
Yep.
There's a reason Frank's here today. No
yes.
electricians in the room, maybe. But
Yeah, so every electrician should be able to understand the report, even if you don't. But yes, most electricians don't. Most electricians will default to 200 amp service. But giving them a report, and the report has the list of products and the websites, you can go buy it. So it's very simple. Like, I'm a civil engineer and I was able to understand the electrical side of it. So it's simple. Send them the report. If they still don't get it, then maybe find another electrician. And if enough people do that, that electrician will learn how to do it. It's using your dollars to incent the industry to move. But it isn't difficult. You're just buying equipment and you're plugging it in.
And related to that question, what about the permit, like the cities? What kind of experience did you have working with them on these projects?
So when I wrote the report, I worked with the City of Calgary. So you should have no problems with the load share devices getting that through the permit process. But I would have them look at it first, or take the permit out, have them look at the permit before you buy the equipment, just to make sure, especially if you're outside of Calgary and the jurisdictions having authority might not have seen it. We're getting, again, this is kind of the pilot stage, getting everywhere, but it's a ULC listed piece of equipment. They can't really say no, or shouldn't be able to say no.
You know what, one of the really enlightening moments I had is when someone was talking to me about, building code officials are not there to stop good projects. They are there to enforce code, which is, as Tanya said earlier, about bringing industry up, the bottom 10% up to the minimum expected requirements. And so the majority of experiences that we've had and with working with the cities on these things is that if you're trying to do new and innovative and exciting things that are getting to higher building performance, it might be a longer discussion, but they're more than willing to have it, right? And so I think that's a really good mindset to go into these types of projects with. Okay. Oh, some more ones coming in here. So a question about district energy and how, this is kind of a bit of an offshoot, but how would either of you say that district energy could fit into this conversation?
You start. Yeah.
I think district energy, depending on how you determine and how you use it, has a great potential to, again, reduce those actual peak loads as we try to move our houses from fossil fuel, natural gas, onto something else. My best use of district energy would be a ground source heat pump loop or a ground source loop that's installed in the alleys that our current natural gas utilities buy or build and own and then sell back to us with transmission or distribution rates. But instead of buying natural gas, we are just basically buying warm fluid that again goes to a ground source heat pump in our house. And the reason it goes in the alley is then there's not a large district plant that has a big operating cost. You just keep building more boreholes as you increase that plant. And then as different houses connect in, they're just basically buying the liters of warm fluid. But yes, district energy of its all different types are a great way to reduce those peak loads because you can move it from one space and have thermal storage somewhere else to kind of, again, shave off the peak and then use it, recharge the system at another time.
Yeah, so expanding on Frank, it's applicable also to commercial facilities, just on a larger scale. With a district system, you centralize all of the efficient equipment and it's operated by a skilled team who knows how to achieve the best out of the equipment for the benefit of the client. Because a lot of tenant owners and clients, they don't specialize in the operation of the equipment. And as the technology gets a little bit more complicated with ground source heat pumps combined with air source, combined with electrification and backup generation with batteries or anything else, managing all that, understanding how all of that ties together for optimal output, sometimes the client cannot achieve that. And having a district distribution system which just supplies warm or cool fluid to the end use for the client to consume can be an effective strategy.
Okay, we've got 1 minute left here. I will perhaps give Frank the last word here. So, and everyone else here who wanted to know what to do with their house, please approach Frank separately. So what devices would you recommend considering for load sharing in a home perhaps where there's no EV or hot tub, so those really big ones? What would you consider looking at interlocking or load sharing?
Well, from what we've seen, and so for those that looking, Retrofit Canada has a bunch of case studies on it. ENBIX has a number of case studies. So again, we're past the pilot stage for these deep energy retrofits. You don't have to reinvent the wheel. You can go and look at these case studies and just kind of pick the one that's most appropriate for you and then find a good local team to help execute it. Sorry, I lost the train of thought. What was the rest?
And I've cleared the question. It was about what loads should you be sharing?
Yeah. If you're not adding a big EV, and you're using a air source heat pump that just replaces your furnace, most of those air source heat pumps will have internal controls. They'll have the electric resistance heater built into it, so they have internal controls that act as a load share. So if you're not adding that EV, you might not need a load share device at all to stay under 100 amps. But there's like 4 in the report. All 4 of the load share devices are more or less equivalent. So I don't really have a preference on one. They're all equally good. But if you're not adding that big kind of additional load, you might not need them if you're just replacing the furnace with like an air handler unit that has the built-in load share device in it. The other thing, I guess, is if you're electrifying your cooking, use a range, not a separate wall oven and a separate cooktop, because again, that's just one appliance as opposed to 2 appliances.
Fantastic. And last time I talked to my electrical engineer, I think we were at about 15 interlocks for a 3-unit place. So you can come and get a prioritized list of me from what works in a few years when I'm in there trying to make a turkey and my kids are having a shower at the same time. I'll let you know how it goes. Thank you very much. This is really informative.